Okay, I know I'm starting a minute early, but we are all here, so I figure we might as well use the time instead of waste it. And first, let me say that Anna did a great job with the little violin duet at church on Saturday. Yeah, appreciated that. So now that we got that out of the way, today is a review lecture where we're preparing for the exam tomorrow. So it's over chapters 4 through 8 of the textbook, 5 chapters. And, well, let's get started. So chapter 4 was where we introduced forces. Anything that pushes or pulls is a force, right? Yes. So we learned about forces. There's the normal force. Why is it called the normal force? Okay, it's normal to the surface. It's named normal force because of its direction. Yes, Isabel. Yeah. Well, it's actually I said yes. It's on already one note.
I don't have one note.
Nobody has one.
I don't have one note. That's a struggle.
You all have a free account with Microsoft.
No, it won't.
Well, then talk to Debbie Intersayer. I mean, I want you to have these resources. I don't put them up there for my benefit. And they are freely accessible to you. You have the technology.
Do you have to know the blocks?
Excuse me?
Oh, wow.
Excuse me?
You have to know the blocks.
No, you don't. Okay. So the normal force is called normal force because its direction is the direction normal to a surface, which is the direction coming directly out of the surface. So if it's the ground, the normal force is coming up because that's the direction out of the surface. If it's the wall, what direction is the normal force? That's right. And if you're on a ramp, which is what you're going to face on the test, what direction is the normal force? Like that.
We are possibly.
Oh, you will.
Do we have to do that X and Y coordinates?
You definitely will, yes.
Like, not perpendicular.
So you have to
Okay, I'm going to jump right to his question just to make sure that we get this covered. When you break things into coordinates, what is your first rule for deciding what direction I'm going to make my coordinate system? Yes. If it has acceleration, make one of them parallel to the acceleration or anti-parallel. Right? That way, the acceleration in the other coordinate direction is 0, which makes Newton's second law in that coordinate direction simple. So that's why you do that. You can do it other ways, but that's going to be the easiest way. We're always looking for an easy way in physics. Hey, yeah, amen. Okay, so yes, you're going to have something with an incline, and if it's sliding down the incline, then you have an acceleration. In what direction would you make your coordinate systems? Yeah, like this. If it's going around on a banked curve, its acceleration is toward the center, so its acceleration is horizontal, and so you'd want to use horizontal and vertical as your directions, even though it's on a slope, because that makes your acceleration in only one coordinate direction. So that rule about the acceleration is key. Okay, so we talked about normal. How do we find the normal force? Okay, its direction is normal to the surface, but its magnitude. What do you say, Claudia? No.
You find the component of gravity acting upon it.
You find, she says, the component of gravity acting upon it. That's still not complete.
What's the equivalent to the forces in the opposite direction? It's just what's keeping it.
Yeah, it's whatever is necessary, so you simply use Newton's second law to find it. There's no other way of getting there. Now, if you have a block sitting on a plane, and there's nothing else acting on the block besides gravity, friction, and normal, then the answers that you guys gave will turn out to be, well, if it's flat, then it'd be mg, and if it's on slope, it'd be, the component of mg that's normal to the slope. But in a general case, like you have the homework problem with a person pushing down on a block, Well, that added to the normal force. Got another one that was essentially the same problem, except for now the person is pulling up. That decreased the normal force. So you have to use Newton's second law to actually find the normal force. Don't fall into the trap of saying, oh, it's just going to be mg, because sometimes it will, sometimes it won't. Okay, force of gravity. I have two forms of the force of gravity here. When would you use the first one, and when would you use the second one?
Second one is the gravitational constant, or whatever it's called.
Well, it's two masses. Try.
Okay, the second one has the capital G, universal gravitational constant. They're both correct in their own realms. The second one is always correct. So you could say, I'm always going to use the second one. But if you're on the surface of the Earth, the radius between you and the center of the Earth is pretty constant, even if you jump up and down. And so we just say that's a constant radius, and the mass of the Earth is constant, so we just take the capital G times the mass of the Earth over the radius of the Earth squared, and we call that lowercase g. So the first form is correct if you're on the surface of the Earth only. And we've just replaced three of the terms in the second one with lowercase g. Now, in terms of direction, what direction is the gravitational force? Okay, down. We define down as the direction of the gravitational force. So that was simple. That's talking about the gravitational force between me and the Earth. What about the gravitational force between Randy and David?
Toward each other's centers.
Okay, toward each other's centers. It's an attractive force. Then we have the force of a spring. That is not the force of a spring equation. What equations did I put in there by accident?
Static friction.
You wrote it in these. It's like potential energy and messed up.
It's the potential energy of a spring. Whoops.
That's not the kinetic energy?
No, that's the potential energy stored in a spring. The force for a spring, it's a vector equation, so I wrote here's a vector. The force is minus kx. K is that constant of proportionality. X is how much the spring is stretched from its equilibrium. And the minus sign is because it's going to pull it back toward equilibrium. So you stretch it, it'll try to pull back. You compress it, it'll try to push back out. And the amount of the force is just proportional to how much you stretched or compressed it. Now, we've talked about friction. There's two types of frictions. There's static friction, when the two surfaces are not sliding against each other. And so people get confused with the car driving. If you're not skidding or peeling out, then your tires are not sliding against the ground, and so you have static friction. Static friction is what makes the car go forward. It's what makes the car stop when you hit the brakes. It's what makes the car turn, static friction. Now, there also is a rolling friction that we won't be concerned with. There is air resistance that you have to worry about with the car. Those bottom two equations are the two equations we had for the air resistance you could have. We didn't go into those carefully. But at low speeds, the air resistance is proportional to the speed. At higher speeds, it becomes proportional to the speed squared. Yes?
On the test, I know we didn't go over like drag or Stokes law that much. Will there be like problems that we need to do concerning them?
No.
Okay.
No, there won't be because we didn't go over them that much. That's actually why they're in italics here. Although on other slides, I just put a line through things that were in the textbook that I may have mentioned briefly, but that won't be on the test. So I won't have you using the Stokes law equation or the Stokes drag or the other drag force equations. Back to the force of friction. I don't know why I shifted onto that. The force of static friction is less than or equal to a maximum value that's mu for static friction times the force normal. So you have to find the force normal before you can use this equation to find what the maximum static friction will be. Now, in our problems, we've done limiting cases, and we'll pretty much stick to that. What's the minimum mu? That means you're going to have force static friction equals mu static force normal. So keep that in mind looking at the words. We're almost always going to ask for a limiting condition to say, okay, when the force static friction is equal to mu s force normal, then what? But the static friction, right now the static friction to act on this box is 0 because there's nothing trying to make it move. It doesn't need any friction to oppose it. If the force of static friction wasn't 0, it would take off for some random reason, right? Force of kinetic friction is the friction between two surfaces that are sliding against each other. So if this is sliding, then there's kinetic friction. Its magnitude is mu k force normal. It's not less than or equal to, it's just equal to. And its direction is the direction opposing the slide. Whereas the direction for the static friction is whatever direction is necessary to keep it from sliding. Yeah.
Going back to like that second equation for gravity, we had to solve like that homework assignment where we were doing experiments and all that everything. Will you give us the like numbers that we need to do them, like
Sure.
how much? Okay.
Yeah. Yeah, I'm not going to ask you to memorize, G is equal to 6.67, blah, blah, blah.
Okay.
The big G?
Okay.
Yeah.
Using these forces, we had Newton's 3 laws. The first law, the law of inertia, that says an object in motion stays in motion unless a net force acts on it. The second law, once you learn the second law, the law of inertia isn't really important because the second law says the the acceleration of an object equals the net force on the object divided by the mass of the object. So if the net force is 0, the acceleration is 0. That's what the first law said. If the net force is not 0, then you can calculate what the acceleration is from the second law. So it's important to know the law of inertia, but we really don't have to ever use it because the second law incorporates, it has it involved. The third law says that for every action, there's an equal and opposite reaction. That's the basic law that says that if I hit the table hits me back with a force that's exactly the same magnitude, but in the opposite direction. And of course, some people are like, well, you hit it hard enough, you can totally break that thing, and then your hand doesn't hurt so bad. I'm still hitting it as hard as it hits me. It's just, apparently, if I can break the table, which I'm pretty sure I can't, I'm pretty sure the opposite would happen. The ultimate strength of the table was less than the ultimate strength of my hand, and so I was able to break it with the force, and my hand didn't break. But I think the reality is, if I hit this hard enough, I would break my hand, some bones in my hand, before the table broke. Because the ultimate strength of the bones in my hand is a little less than the ultimate strength of that tabletop. Okay. So I have to be able to apply the second and third laws as necessary. You don't have to say, oh, the second law says this. You can just say, applying sum of the force equals mass times acceleration. Right? You do need to be able to do that. Be able to draw a free body diagram. I actually drew this the first time in my life, I think, that I've drawn free body diagrams on all of those problems I did for the worksheets. You guys know that you can see the solutions on YouTube, and you can see the solutions of the workout stuff on OneNote. I'm sorry. Okay, so make sure you can apply Newton's second law. Why do we make a free body diagram? The free body diagram is actually to help us in applying Newton's second law. Remember a free body diagram is you're drawing all the forces acting on the object you're interested in. And then Newton's second law says the sum of those forces has to be mass times acceleration. So if we have more than one direction, we break them into components. So make sure you're good with breaking things into components. I have modeled over and over again. I have my x direction, my y direction. I break my vectors into those components. So then I can apply Newton's second law in each component direction independently. Questions on chapter 4? And chapter 4 is like, you got chapter 5 and 6, that's just more application of chapter 4, really. So any questions about that? Okay. Moving on to chapter 5. Steps for problem solving, because that's what chapter 5 was. Okay, how do we use this stuff? So draw a diagram to illustrate the problem. Remember for the synthesis problems, if you're going to get partial credit, you're going to need to have a diagram that's a useful diagram. Right, just a diagram that's not relevant, or a diagram with errors, those lose you some points there. Then identify the object or system you're interested in and draw a free body diagram. Because you're using Newton's second law, you want the free body diagram. If it wasn't Newton's second law, you probably wouldn't need to have a free body diagram. Then identify your coordinate system, remembering our rules. If you have acceleration, choose a coordinate system so the acceleration is in one of the directions. If you don't have acceleration, then choose a coordinate system that's easiest. So if I have two forces that are perpendicular to each other and a third one that's not, I'll choose the direction where those two are already resolved and I don't have one left to resolve. Because that's less work. Always trying to do it the easy way. Then apply Newton's second law of motion in each component direction and solve. And of course, make sure your answer does make sense. I forgot who it was. I was doing a homework problem with, it was Oksana. And we did a solution and I'm like, well, that doesn't make sense. And I'm all frustrated. And then we look at part B. Why doesn't this answer make sense? Oh, I guess I should have. Should have not stopped at the that doesn't make sense part. Okay, chapter 6, circular motion. And it has elasticity, but you are not going to have elasticity. So circular motion. This is where we had to start doing things like, oh my goodness, rotational kinematic equations. We didn't do too much on that, but I guarantee you I don't know, I have finished writing the test. I think it's more than half written. But you probably will have a problem where you have to do something with rotational kinematic equations, like on the worksheet. So what's the difference in the regular kinematic equations and the rotational kinematic equations? Yeah, the song's the same, only the words have changed. You have the same equations, it's just instead of V, you have omega. Instead of velocity, you have the angular velocity. Instead of acceleration, you have alpha. As instead of acceleration, you have angular acceleration. And instead of position, you have theta, angle. Otherwise, the equations are all the same. So if you could do kinematic equations before, you can still do them now. There is one thing that can be confusing about this. When we're talking about the circular motion, we have the correspondence between speed and angular velocity. Speed is omega r. This speed is what we call the tangential speed, the speed at which something is going in the direction of the rotation. You could have a situation like, I don't think this will give away too much on the test. You have a problem. Everybody know what tetherball is? You have a problem on the test that involves tetherball, where you have a ball hanging from a rope that goes around the pole. So now that I think about that, I have a hard time coming back to this. What was we talking about?
Angular acceleration.
Okay, yes. So in that case, when you're playing a real game of tetherball, this here is just all going around the circle on the test. But a real game of tetherball, as it goes around, it wraps up on the pole. And so the radius is getting shorter. So you have a component of the velocity that's coming toward the center that we call the radial velocity. And you have a component that's tangential that's going around the circle. And this equation is only the tangential. And likewise, you can have, so sometimes we'll put the t there to be clear. The tangential acceleration is equal to the angular acceleration times the radius. So in one of the worksheet problems, you have to calculate the total acceleration. And if you have something going around in a circle, you know it has to have a certain acceleration toward the center. What do we call that? Centripetal. Centripetal means toward the center. So it has to have an acceleration toward the center that is v squared over r, or omega squared r. So the centripetal acceleration is, I'm going to change color just because I can, so it stands out actually. So you have the centripetal acceleration toward the center and the tangential acceleration in the direction that it's moving. And if you wanted to find the resultant from adding those two perpendicular vectors, you use the Pythagorean theorem because you're adding vectors. And perpendicular, well, that's how tip to tail. Remember that. Okay, so we have this circular motion. We were only doing rigid objects, doing circles. That's why we didn't actually worry about saying VT and AT, because we're doing rigid objects. But starting with the next chapter after the test, stop crying, we're going to have rotating objects that don't stay at a constant radius, and then that's going to be an important distinction. So I've already talked about the top two. Centrifugal force. Everybody, I think, correctly identified centripetal acceleration. Centripetal acceleration being the acceleration necessary to keep something going in a circle, and its direction is toward the center of the circle as it goes around. Centrifugal is a, quote, fictitious force. Fictitious because in an inertial reference frame, a reference frame where Newton's laws work, remember the first law is the law of inertia, and what that means is has to be no acceleration of your reference frame. So if you're in a car and the car is accelerating, the laws of physics don't work quite the same as they do in the laboratory simply because your perspective is wrong. Somebody standing outside and watching you accelerate would be just fine. So if you're in an inertial reference frame, there is no such thing as a centrifugal force. But if you're in a roller coaster, let's do that little dropout ride they have where it spins in a circle and the floor drops out and you stay put. Why do you stay put? Okay, not out. You're being pushed in because your body's trying to go straight, but that wall keeps pushing you in, creating a force normal that, of course, has nothing to do with G, right? And that normal force that's pushing you in, we would call the centripetal force. The force pushing you toward the center that is necessary to keep you in a circle. So on a free body diagram, the centripetal force doesn't show up. The force normal is on the free body diagram, and when you add everything toward the center, that is the centripetal force. And then you have the force of friction because the force normal is there, and that's what keeps you from sliding down. So the centrifugal force, if you're riding that, it feels like what Claudia said. It feels like you're being pushed out. And so that's what the centrifugal force is that feeling like you're being pushed out, when in reality, you're trying to go straight and you're being pushed in. Coriolis force is also fictitious. The Coriolis force is the fictitious force responsible for the rotation of hurricanes and tornadoes. And once again, anyone who's got a brain in their head says, how can a fictitious force be responsible for the rotation? And it's because calling it a force is incorrect. It is something that happens because of the changing speed as you increase radius. As per that top equation, V is omega R. If R gets bigger and V is constant, or excuse me, if R gets bigger and omega is constant, then V has to get bigger. The truth is this, if I throw a ball, the V, if I throw a ball north, the horizontal speed, the east-west speed stays the same as long as it's in the air. But the radius could change if I threw it a really long distance, not my arm, but a cannon now. And thus, compared to the Earth, it would appear to speed up in the direction the Earth is rotating, which is toward the east. Yes?
What's the subject again?
That was tangential. It means in the direction of motion. Okay. Why is centripetal force never placed on a free body diagram? It's a fictitious force. It is simply the resultant. You don't draw the resultant force in a free body diagram. You draw the actual forces, and then when you add them together, that's going to give you the centripetal force. All right, chapter 7, work, energy, and power. So, energy. We've used this correctly. You you go and you work out really hard at the gym, and then you come home and you're like, I don't have the energy to do any homework. We've all had this experience, right? Yes. That's accurate to the meanings of energy and work, because energy is the ability to do work. If you used up your energy at the gym, you don't have any energy left to do work. Now, of course, doing homework probably isn't going to require too much energy, but it does require some concentration and whatnot that's also going to be lacking when you're exhausted. So energy is the ability to do work. We have two types of energy: kinetic energy, energy something has because it's moving. If a ball is flying toward my face, I'm pretty sure that when it hits my face, it will do some work on my face. So it has the ability to do work because it's moving. So we call that kinetic energy. If I hold a bowling ball above my head, I also am pretty sure that it has the ability to do work on my head because of its position. If I let go, it'll fall down and do work on my head. We call that potential energy when it has the ability to do work because of its position. So potential energy is only associated with conservative forces, forces that will give back energy. What are some examples of conservative forces? Gravity. Gravity is a conservative force. So that means we have a potential energy due to gravity. That is mass times gravity multiplied by the height. Now remember, work is force dot distance. That's force times the distance parallel to the force. So if I push on this table, I'm actually pushing on it, but it's not moving. Am I doing work? No. Now let's be clear, I'm not doing any mechanical work. I am expending some biological, some chemical energy, so there is a certain amount of metabolic work going on. But mechanical work, which is what we talk about in physics, there's no work because the distance was zero, even though the force wasn't zero. Now, since you gave me this Sharpie to deal with, by pushing the Sharpie and it moves, am I doing work? Yes. It stopped. Why did it stop? Okay, I stopped doing work on it, but there's something else. Friction. Friction was also doing work. It was doing a negative work because it was sliding that way against the tabletop. So the force of friction was this way. The motion was that way. They're opposite directions. So when you do force times distance parallel, if the distance is in the opposite direction, that's a negative work. So friction was doing a negative work. I was doing positive work. When I stopped my work, friction took away all of the energy that I had put into it, and it stopped. So friction, not conservative. It didn't give back the energy. Okay, what's the second example of a conservative force? One that will give back energy. A spring. A spring is another one. So that's why we had the potential energy equation. I accidentally put as a force for the spring. Where was it? All the way back here. That 1/2 kx squared is how much energy is stored in the spring. So when you compress it, x is a negative value, but when you square it, negative value squared is positive, and it's going to have potential energy stored in it. When you stretch it, then x is positive value squared is still positive. It again has a positive potential energy. Yeah, this is the right one. So, springs, gravity. You know what? At this point, those are the only two conservative forces we know. We have electric and magnetic. We saw in lab the magnetic force was conservative. It gave us back our kinetic energy in that case. So those are also conservative, but we don't deal with those at this point. So as far as we're concerned, I talked about conservative and non-conservative forces, and non-conservative things like friction or the work done by a motor or by a person pushing. Well, we only have two conservatives, the spring and gravity. So we're probably easy to remember those two, and if it's not one of those two, then it must be non-conservative as far as we're concerned. Be able to calculate the work. Remember, direction matters. My example of carrying something, moving at a constant horizontal velocity and applying a constant upward velocity, the work is zero because the force is perpendicular to the motion. So make sure you have those ideas square in your head. Graphically, if I have a force function and I have that force acts over a certain distance, then I can't just say force times distance because the force is changing. But if I take a whole bunch of tiny little boxes and do force times each tiny little distance, those would add up to the total work. And this is the first step you do to learning how to do an integral in calculus. It turns out that the area that you have under that curve is equal to the work. So if I have some random function, like let's take the way a bow, I'm sorry, I can't draw very big on here. If I have a compound bow, the actual graph for force as a function of how much you have drawn it back is different than you might expect. It goes like that. So at the very beginning, as you pull, the force increases with distance. But then it's just a hard pull all the way back until you get to where you're going to hold it for shooting, and then the force drops off. Has anybody ever observed that? Anybody ever use one of these bows? A couple people. Can you think of why they would do it that way?
Because it takes a lot of energy to actually hold it if it's pulling that hard. So
Right.
let it relax a little. So
You're back here, even though you're not doing any work mechanically, you still have that work that's necessary to hold it. And so they make it so it's easier to hold back here when you have it fully drawn, so that you don't get tired while you're aiming, and so you're not shaking with fatigue as you try to aim. But why do you have it go up to a high value and stay roughly constant during the draw? So that, never mind. Well, what I was just saying was the work is the area under the graph. And so making it go up to a high value and stay up there allows you to get a very large amount of work done to draw it back. This is essentially a spring system. It's going to return that energy to the arrow.
So the bigger the area under it.
And so the bigger the area under it, the more energy you have stored in the bow. And so in a case like this, you would just try to find the area under here to say how much energy is stored in the bow. By the way, how do they accomplish that? Oh, ye engineers. How do they accomplish that funny force versus distance drawn relationship?
Yeah.
They use cams. They have off-center pins on the cams so that it pivots about a different point. That's how they make it happen. Well, that, and they actually have a complicated way of running the strings as well. Cams are, ovals or loops that are used in machines. Okay, be able to work out work energy relation problems. So what's the first thing you do when you're working? I don't think I have the steps. Oh, I do. Okay. First thing you do when you're working out a work energy problem is draw a diagram to illustrate the problem. And as we have in the worksheet, I have the beginning, the intermediate, and the end states. So you want to make sure you have each important stage illustrated in your diagram. Then identify the energy at each important point. Now, when I say the energy, that is both the kinetic energy and the potential energy. Now, I need to determine if there is any non-conservative force. And if there is, try to calculate what that non-conservative work is. And then I use the work energy relation in that form. Now, there are two forms that we've seen of the work energy relation. They are equivalent. One is that the net work is equal to the change in kinetic energy. Now, that's the net work. All things that are doing work added together.
Wait, what is W in, what is that?
What I just wrote or the one that's written?
No, what you just wrote.
That's NET, net.
Oh, okay. I'm so sorry.
No, it's okay.
Okay.
I know, my handwriting is not Not going to win any prizes.
Somewhat of
Somewhat. So the network is the change in kinetic energy. But the network we can break up into two pieces. The conservative work, the work done by, at this point, gravity and springs, and the non-conservative work done by things like friction and motors and humans. And we define a potential energy only for the conservative work. And the potential energy is actually defined as work conservative equals minus the change in potential energy. Oops. And so since net work would be work non-conservative plus work conservative, replacing work conservative with minus change in potential energy, that gives you the relationship work non-conservative is change in kinetic plus change in potential. So the blue equation and the black one are exactly equivalent given the definition in red. So for solving work energy problems, we usually use this form. But if there's no potential energy involved, then we'll stick with that one. So sometimes we use one, sometimes we use another. Either one is correct. It's just which one's going to make life easier. Make sure your answers make sense, of course. It's the last step. Solve it, make sure they make sense. Finally, chapter 8. That's where we dealt with momentum and collisions. So notice I crossed out be able to describe and calculate the position of the center of mass. You're not going to have to do that. You should know what's important about the center of mass, though. What's important about the center of mass? There's lots of things, but what am I looking for? Yeah, this is no fun. This is more fun. What's important about the center of mass this thing? Okay, it is going to be closer to the top. I say you don't have to remember how to calculate that, but yeah, the center of mass is somewhere around here. It's going to balance if I put my finger under the center of mass. Why? Because we can treat it as if all of the force of gravity is acting just there at the center of mass. Furthermore, if I take this and I toss it to David, will you not hurt yourself if I toss this to you slowly?
Yes.
Okay. If I toss it to David,
That was a bit fearful.
if you're watching the end of it's moving up and down as it goes through the air, right? But the center of mass was following the perfect parabolic arc like we learned earlier. The center of mass, it's not. My vision's not good enough, is the honest truth. I can catch balls because they're big, and I just put my hand where they're coming. But with this, I'd be like, it's not like my vision's bad, but it's not good. That's why I stopped playing single league softball. So the center of mass is important because we can treat things like force of gravity as act on the center of mass. And in something like a collision problem, the center of mass, if momentum is conserved, the center of mass just keeps moving with constant velocity. Okay, know what linear momentum is. Mass times velocity. Velocity is a vector, so there's a directionality to it. It's not just mass times speed. When is linear momentum conserved? Under what two conditions is it conserved? Okay. The net external force is 0. Yeah. What's the other one? No time. Those come from Newton's second law. Newton's second law says the net force is equal to change in momentum over change in time. This is a vector equation. I'm just writing it without the vector signs for purposes here. So if I solve that for change in momentum, it's the net force multiplied by change in time. What do we call the right-hand side of that equation? It won't be on the test, by the way. Yeah. The right-hand side is called the impulse. And what's the left-hand side called? Change in momentum. So the change in momentum is 0 if the impulse is 0, which means if the net force, what Max said, is 0, or if the time is 0, which I don't know who said that. Okay, Sarah said. So either of those cases will conserve momentum.
Either one or both of them together?
Either one.
Okay.
which is why we typically say that a collision, like a car collision, where the net external force is most clearly not zero, has momentum conserved during the collision because the time for the collision is so short. So momentum is not conserved up to the collision, not conserved after the collision, but during that instant collision, it is. So in the worksheet I did, there is a ballistic pendulum problem, which is a bullet comes and hits a wooden block, embeds in the block goes swinging up. During the collision, the time it takes from when the bullet first strikes the wood until the bullet is embedded in the wood and the bullet and wood are moving together is very, very small. So we say that momentum is conserved during that period. Now that is actually special because the net external force in the horizontal direction was also zero. So even if it took a while, it would still be conserved there. But in car crashes, it wouldn't be, except for the time so short. Okay, elastic versus inelastic. As far as we're concerned, elastic means completely elastic. You don't lose any kinetic energy. So when two things bounce off of each other, in reality, you're going to lose some because nothing's perfect. But for our general physics purposes, we're just trying to learn principles, and so we say they're going to be completely elastic if they bounce off of each other, which means kinetic energy is conserved. The other side of the coin is completely inelastic. Of course, it's really easy for me to mix these words up myself. Completely inelastic means they stick together. So the example with that ballistic pendulum, they stuck together, it was completely inelastic. In that case, kinetic energy is going to change, but your final velocities are the same. Be able to solve one-dimensional collision problems. Don't have to worry about two-dimensional collision problems, but one-dimensional. And an example of a problem. Any questions before I go to working a problem?
How much of a test do you think is going to be on chapter, the one with the radius and speed things and the W theta? Yeah.
It should be roughly 20%. Right, just a breakdown. Each chapter should be roughly 20%. Although, like I said at the outset, if you learn chapter 4 carefully, that's going to help you through 5 and 6. And so chapter 4 is probably the most important single one because that's a concept that's continued on in 5 and 6. Okay, so collision problem. A 3.33 G, what does G stand for? Gram. Just making sure we're clear here. Not, 3.33 times the acceleration of gravity. With initial velocity of 125 meters per second east, that's a fast speed, collides elastically with a 425 gram object, initially traveling at 2.25 meters per second east. That's a much slower pedestrian speed. So basically we have a bullet hitting a, let's say, softball. Not a person. No. Wait. Okay. I somehow didn't even hear what happened. I feel guilty nonetheless. What are the final velocities of each object after the collision? So first of all, what type of collision is this? Elastic. If it's elastic, what rules do we have in place? No kinetic energy is lost. So I draw my picture. Object 1, moving it. That was a very nice arrowhead. V1 initial equals 125 meters per second. And then I have object 2 moving at V2 initial equals 2.25 meters per second. So there I have everything before the collision. Then I have the collision, and I will have, if they collide elastically, what do you expect object 1 to do? Slow down? I expect it to bounce back because it's so much lighter. So I'm going to put here velocity 1 final. And what's going to happen to object 2? It's going to speed up a small amount, right? Russell, question?
What if it's pointed?
What is what?
What if object 1 is pointed?
Object 1 is going to be it's going to be a one-dimensional collision. I think I specified that, didn't I? I didn't say one-dimensionally, but it's supposed to be one-dimensional, which means it has no option except for to bounce straight back. Okay? Just remember that when you read on the test. You don't need to ask that question. I know on the test it says collides one-dimensionally, so you don't have to ask, what if it bounces off in some crazy direction?
No, I wouldn't ask that.
I thought you would.
If it was pointed in such and such, to the second object.
If it's elastic, it's still just bouncing off and not causing any damage, because if it caused damage, that would take away energy and that would be partially inelastic. All right, so I've drawn a picture. What do I do after my picture if I'm solving a collisions problem? That's a good question that I should answer. All right. I mean, hey, we're here to make sure we're ready for the test, not for me to quiz you yet. That's tomorrow. So we're going to have two conditions: conservation of momentum and conservation of energy. Now, we can work this the hard way or the easy way. I'll tell you, I won't have the equation for the easy way on the test, but I won't mark you off if you remember. Yes, Oksana. Okay, the work energy problem here, we would have too many unknowns to do it that way. Right? We don't have any potential energies here, so we don't have to worry about that. But we have kinetic energy 1, kinetic energy 2, kinetic energy 1, kinetic energy 2, the initials and the finals. That gives us one of our two relationships, but we can't just do that. We have to have two relationships because we have two unknowns. What are my two unknowns? The V1 final and the V2 final. So I have the equation Oksana was just quoting. The energy initial is energy final. There's no potential energy, so I didn't write those PEs in there. So that's one equation.
Is that the easy way?
No, that is the correct way, and it was from manipulating this equation that I got to the easy way.
Wait, what?
Conservation of energy, because there is no potential energy.
They're both moving, that's in the last equation.
There's no change in elevation, there's no springs. Okay, so kinetic energy of the initial, so the two starting is equal to kinetic energy final. That's what that is. And then I could substitute 1/2 m1 v1 initial squared plus 1/2 m2 v2 initial squared equals 1/2 m1 v1 final squared plus 1/2 m2 v2 final squared. And we are all plenty smart enough to say, let's multiply everything by 2, get rid of the 1/2s. You are plenty smart enough for that. Yes, we're sure. Then the next step and so I'm only doing the kinetic energy part right now, not the momentum yet. The next step is to move mass 1s on one side of the equation, mass 2s on the other. Instead of having initial versus final, we'll have 1 versus 2. And so have mass 1 times V1 initial squared minus V1 final squared equals mass 2 times V2 final squared minus V2 initial squared. So there I've moved this term to that side and this term to that side. Well, I'll show one step further just as a reminder. We said, ooh, you can do the whole, I can't remember the math term because apparently I'm senile. You remember me doing that? Yes, good. Now I have to stop here and go to the momentum equation before I can continue. So the momentum equation, momentum 1 initial plus momentum 2 initial equals momentum 1 final plus momentum 2 final, or M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. If we take this equation and we likewise bring the terms by mass, we have mass 1 times V1 initial minus V1 final equals mass 2 times V2 final minus V2 initial. So that's my equation for conservation of momentum. And if I take that, I see this here and this here are this and this. And so I can cancel those, so my kinetic energy equation becomes V1 zero plus V1 final. And so that's one equation I used to solve it, and this is the other equation I used to solve it. So the easy way, what I said is I won't mark you wrong if you remember this equation that's in the blue box down here. But you can see where it comes from, just conservation of kinetic energy if it's an elastic collision. Now with all of that said, I'm out of time. But now I have two equations, the two in the boxes, two unknowns, V1 final, V2 final. So I just solve one equation for, let's say, V2 final, and then plug that into the other equation to eliminate V2 final and solve for V1 final. So I'm out of time, so I must stop. Have a great day. I'll see you in lab tomorrow for the exam. And Diana, you had a question? Well, the easy way is to start with this equation. The hard way is to start with this equation. Right, so this here was the work that was additional in doing it the hard way.
Why wouldn't you put the easy equation on the test?
Because it's not a generally true equation. And I only put generally true equations on the test. Same reason I didn't put the, quote, range equation on the test, because it's not generally true.
So if I remember that equation,
Yeah. Right, that's what I'm saying. You remember that's only for elastic collisions. For any elastic, you have V1 final equals V2 final. That's easy. That's your question.
I was going to say, that's only for elastic.
Right.
What about any elastic?
In any elastic, you have V1 final equals V2 final. It's a much simpler second equation. So you still have this equation for all collisions that where momentum is conserved. And if it's inelastic, V1 final is equal to V2 final.
Dr. Witt,
Yeah.
finish this one?
Sure. Yeah, the class is over. Leave if you have to, but I will finish it and it'll be on the recording so you can watch it on YouTube. On YouTube. So, let's just do it algebraically. Let's solve for V2 final equals V1 initial plus V1 final minus V2 initial, and then put that into there. So I'm going to have
My fault. Where's Idaho? Tell me where it is.
Is torque gonna be on the test?
no.
Oh man. We don't know.
That's chapter 9. That's why the homework is not due tonight, but due on Wednesday, because we're,
I was like, what I should say.
Okay, so what I've done now is I have substituted in this bracket for V2 final. And I distributed on the left side, but I didn't distribute on the right side yet because I didn't want to confuse the substitution and distributing at the same time. Well, you still have to be able to do from what I'm doing now, from what we're doing after the class ended, right? Because that's no longer the derivation, that's just doing the work. So now I'm going to distribute the right side. So now I'm solving for V1 final. So I have V1 final here and here. So I'm going to move this across, which means I better move those two over. So I have M1 V1 initial minus M2 V1 initial plus 2 M2 V2 initial equals M1 V1 final plus M2 V1 final. Factor out the V1 final on the right-hand side. And then I just need to divide everything by M1 plus M2. So dividing everything by M1 plus M2. I end up with V1 final is equal to that equation, and then I just put in my numbers. So in this case, that would be equal to 3.33 grams minus 425 grams times 125 meters per second plus 2 times 425 grams times 1. Oh, that can't be 125. What was it really? Oh, it was 125. It's the speed is 2.25.
So when you say memorize the bottom, what do you mean?
Well, I'm saying if you memorize this equation in the box, if I have an elastic collision problem, one-dimensional elastic collision problem, you can use that.
And we don't have to explain how we got it.
Right, you can just say the conservation of kinetic energy combined with conservation momentum gives me this equation and go from there.
I guess I was just used to an elastic collision, but you're using the momentum.
Yeah, they're easier, right?
Yeah, okay.
Okay, so now we've got all these numbers in there. We got to pop them in the calculator. I don't feel like it. I mean, at this point, all you have to do is put in the calculator, and you'll get the speed for V1 final. And as you can tell, 3.33 minus 425 is a very big negative number, so it's going to be going backward.
This is gonna be on YouTube.
Yes, it will.
It'll be on OneNote.
Yes, it already is on OneNote. Okay, and then once you have V1 final, then you just come back to where I had solved this V2 final in terms of V1 final, V1 initial, V2 initial. My wife